Swayam Prabha. Digital India. Educated India.
All right. So, good morning, good afternoon. Welcome to this series of lectures we've been going through on analysis and design of rigid pavements. As a reminder, we are in module 2 of these lectures. So, module 2 is the analysis of rigid pavements using classical methods. What classical methods basically means is that those are methods which don't require any sophisticated computer implementation. We generally get nice and easy formulas whose values we can then calculate maybe by hand, perhaps with a calculator. We might be able to implement it on a spreadsheet at most. But there's no need to write any sophisticated computer code in order to analyze it. I should add, these classical methods are not what are done in today's practice in engineering. Today in engineering, we like to use complicated computer codes using something called the finite element method to do these calculations. But it's important to understand the classical methods and the shortcomings before we jump immediately into the finite element method. So that's why we're going through module 2. And in module 3, we will go into the finite element method, and I'll give you more discussions over there. Now, as a reminder, within module 2, we've been going through a series of lectures where we are talking about temperature and moisture, or in general, climatic effects on rigid pavements. So, rigid pavements are outdoors. I think that's obvious. Rigid pavements are outdoors. So, everything that all of us know about weather and climate affect rigid pavements. The fact that it can be very hot today and then we can have some pre-monsoon showers and can start raining the next day. The fact that it does get cold over time and winters in many parts of the country can get cold. The fact that India is a very large and diverse country. We have different amount of solar radiation coming in different locations, and it is not purely just a function of latitude. All these things together mean that the effect of climate on rigid pavements can be rather complicated. And as we saw in the previous lecture, one particular aspect of climate, namely temperature, can actually lead to significant amount of stresses developing. So we saw that when we have a pavement which has some temperature distribution generated in it, in practice, that temperature distribution is going to be nonlinear, and then that is going to have certain stresses developing in it. Those stresses come because of the fact that under a nonlinear temperature distribution, the slab would expand or contract. Now that generally leads to a very small amount of stress. It comes from base friction, so mostly we don't account for it. Then you also have a situation where you have a linear temperature distribution, which is what we call curling. When you have curling, the pavement wants to assume either a convex or a concave type of shape. But when it wants to assume that shape, it can't. It is restrained. It is restrained because of self weight. It is also restrained because of any external loading which is applied, namely from vehicles, which we'll always have in pavements. And so that leads to development of certain stresses, which we call curling stresses. But we also saw that for nonlinear temperature distributions, we have an additional source of stress. That source of stress basically comes because in the medium thick plate theory, which we use to analyze rigid pavements, plane sections which are perpendicular to the neutral axis before bending remain plane and perpendicular after bending. That is a very important assumption, and there's been a lot of data and research which has shown that this is a good assumption for rigid pavements. So, under that situation, when you have a non-linear temperature distribution, then the cross section wants to assume a non-linear shape, but due to this kinematic constraint, it is unable to assume that shape, and therefore it is restrained from deforming non-linearly. That restraint then creates an additional source of stress, which we call self-equilibrating stress, non-linear stress, or more generally, eigenstress. So as we saw that when we have temperature distributions, which we almost always have, when we have temperature distributions through the rigid pavements, we can have curling stresses as well as eigenstresses. And those stresses affect the performance of the pavement. What I want to talk about in today's lecture is another effect, namely the effect of moisture. So what I had mentioned in the first of these series of lectures is that when the pavement is exposed to moisture in the short term, in the long term, which basically means flooding or precipitation, in the long term, if the pavement is maintained properly, that is, all cracks are sealed up, joints are maintained properly, then generally there's no effect of moisture. But in the short term, when the pavement is, say, in the first 3 days of its development, when the strength is still relatively low, then due to the fact that the pavement itself has a certain humidity, generally you can assume that it's saturated. But then above the pavement, you have the ambient humidity, which, unless it's raining, is not going to be saturated. Because of a sharp difference in humidity between the above the surface of the pavement and below the surface of the pavement, you have additional stresses which develop. These lead to what are called shrinking stresses. Furthermore, talking about early age behavior, there are also temperature distributions which are developed at the early age of the concrete, which also have to be accounted for when we are considering the effect of temperature on rigid pavements. So, in today's lecture, we will look at both these phenomena. The first, which is related to moisture, is called shrinkage, and the second, which is related to temperature distributions in early age concrete, is called built in curling. So, in today's lecture, I will formally define shrinkage. We'll talk a little bit of how it's calculated and how we can use it to estimate stresses. In particular, we will look at one particular model, which is a fairly useful model in pavement engineering, called the Bajant and Baweja B3 model for shrinkage. And then we will define and quantify built-in curling. Okay, so let's go back and recall a little bit about how the pavement is initially. So, what is the concrete pavement? Basically, it's a slab of concrete. So, concrete again was cement, aggregates, maybe some supplementary cementitious materials, and water. We mix them together, and initially, it's basically in a liquid state. What that means in a liquid state is there's no additional stress as such developed in it. So, we pour it in the form of a slab, and then generally we can assume that it is saturated, that the RH inside the pavement is around 100%. So this moisture is required for hydration. If we actually don't provide adequate moisture inside the pavement, then we will not have adequate hydration, and therefore we will not have adequate strength development. So it's very important that this relative humidity is actually about 100%. But above the pavement, in the general atmosphere, a relative humidity of 100% basically means it's raining. And well, if you should not be constructing pavement when it's raining. So generally, during the early age of the pavement, you're not going to have a relative humidity of 100% in the atmosphere. If you're in a coastal area and it's fairly humid, your humidity can be maybe 90 to 98% even, quite humid. If you're in a very dry desert type of area, your humidity might be 40% or even lower. And in other places, you'll have some values in between. So if we consider just the surface of the pavement, below the surface, you have an area of basically saturated condition, that is, your relative humidity is 100%. Above the surface, you have an area where the relative humidity is less than that value. And so a humidity gradient has been set up. The interaction between the atmosphere and the PCC surface will therefore cause a moisture gradient to develop. What basically happens is that very close to the surface, very thin distance, around maybe 50 millimeters or 25 to 50, but very short distance into the surface, you are below that, you're going to have an RH of 100%. Exactly at the surface, you're going to have an RH equal to the ambient, let's say it's 90%. In between, in this very thin region, you're going to have a sharp change, and it's going to be a very non-linear change. You're going to have a sharp change in the humidity or in the moisture. That therefore is called a moisture gradient, and it's a very sharp moisture gradient. These moisture gradients will then lead to develop of additional stresses or strains, which we call shrinkage. So the moisture gradient leads to development of stresses, and this phenomenon we call as shrinkage. If we leave this phenomenon unchecked, so this is inevitable, it's going to happen because you're never going to have an atmosphere which is 100% saturated all the time. But the pavement, the concrete itself should be saturated initially when you mix it with water. So you are inevitably going to have this gradient set up. If we don't do something about this gradient, that is, if we don't take some measures, we'll talk about what measures in the next slide, but if we don't take some measures to offset the effects of these, then very early in the service life, we will have a series of crack swaps. So what will happen is we'll have a situation where we have a sharp moisture gradient, Because of the moisture gradient, some amount of strain is going to be developed, and that strain is going to create some amount of stress. If And that stress can actually be quite high because these strains are very high. Because these gradients are very high, the strains can be very high, and so the stresses will be very high. At an early age, approximately 3 days, the compressive strength of the concrete is very low. So these strains, they may not be too high relative to the 28-day strength, but relative to this 3-day strength, they can actually exceed the strength, in which case you're going to have cracking. So if you don't control for shrinkage, what you will see is that within the first 3 days, before any traffic has gone on the pavement itself, you will see a series of these thin, narrow cracks forming all over the pavement. It'll be a long series of cracks. Now, on its own, you might think that those cracks are okay. They're generally very thin. That means that the crack opening width is very small. The problem is that once a crack has begun, they create a path for moisture ingress. And so now that you have some cracks on the surface, some amount of moisture is going to come inside, and you're going to start having a cascading series of effects, and more cracks are going to be formed as a result. So these shrinkage cracks, which are caused very early in the service life, can compromise the entire service life of the pavement. So generally, we don't want them. We have to do something in order to control them. Now, shrinkage cracking can be controlled through a process called curing. I'm sure all of you have studied this in your structural engineering classes. The same principle applies to rigid pavements. Curing is basically a process where we saturate the surface also with moisture. So instead of the surface being exposed to the atmosphere, we somehow create a film such that the moisture gets locked inside and the surface is not completely exposed to the atmosphere. That process is called curing with respect to rigid pavements. There are generally two types of curing. That is chemical curing, which is sometimes also called sealing. And then we've got physical curing, which is also sometimes called water curing. So chemical curing is a process where we basically take a certain chemical and we dissolve it in a solvent. Most common solvent is water. So we dissolve a certain chemical in the solvent and then we spray a thin layer of this chemical on top of the slab. I've got an image over here taken from the US Federal Highway Administration where you can see this gray part of it, which is the original concrete which has just been laid out, using this machine which is called a slip form paver. So using a slip form paver, the concrete is laid and then the paver has some additional nozzles which also sprays this curing compound which you're seeing in white over here. So this curing compound is some type of a chemical which has been dissolved generally in water and is sprayed all along the surface of the concrete. Now, what happens over time is that the solvent not dissolved, the solvent evaporates. So the solvent, which is water usually, it evaporates. So the chemical just forms a very thin powder-like coating on the surface. This thin film then seals the moisture inside the slab. So the main important property of this chemical is that it should lock in moisture. It should not allow any amount of moisture to get out of the surface. So it seals in the moisture in the slab. That's also why chemical curing is called sealing. So it seals in the moisture. So it guarantees that the surface is basically never exposed to the ambient environment, and so no moisture is able to go out and establish these sharp moisture gradients. That's how we reduce shrinkage. Now, chemical curing is a very nice technique. It's been shown to be very effective, but there are many question marks on a variety of choices which can be made and their effect on the effectiveness of chemical curing. So, for example, the application rate and time. So, in this picture over here, the application rate would be per second how many milliliters of the chemical is being sprayed per second. And then what is the application rate? In other words, how fast is the slip form paver moving? What should be the thickness of the film? Of course, it will be in microns, but 1 micron, 10 micron, 50 micron, because the main purpose of this film is to lock in the moisture, to prevent any moisture gradient from being established. So what is the suitable thickness of the film, which ensures that that indeed is the case? And what about uniformity? In practice, now, when we have a slip form paver, mostly we'll get a relatively uniform distribution. So if we actually measure the thickness of the solvent at various points, we might get a distribution which might look somewhat like this. So we will have a distribution. It won't be the same everywhere, but it will be a fairly narrow distribution or a uniform distribution. In many cases, however, if we are not using a slip form paver or we don't have a slip form paver which has these nozzles, then it has to be done manually. That is, somebody actually has to wear this belt and jacket on their back which contains this chemical, and they have to physically spray it. It looks very similar to spraying fertilizer in a field, for example. In that case, you'll have a large variety in the film thickness, so the distribution might be much flatter and wider, for example, as I've drawn over here. So the question is, what sort of uniformity is acceptable to lock in the moisture? How is that uniformity affected by application time and rate? What is the film thickness that we should be aiming for that will sufficiently lock in the moisture, but at the same time minimize the use of this curing compound, because it is an additional cost. It's not cheap to use this compound, so it is an additional cost. Those are the open questions in the field of chemical curing. The other type of curing, and this is a picture I actually took from IIT Gandhinagar itself, the other type of curing is called physical curing. Sometimes we also call that water curing. Now, this basically involves using water to keep the surface of the slab moist. So the principle of chemical curing was to lock in the moisture on top to create an impermeable seal on the surface and keep the moisture inside. The purpose of physical curing, however, is not to put a seal, but actually to saturate the surface itself. So the surface is not actually exposed to the atmosphere. We have a layer of water, which is at 100% saturation by definition. We have a layer of water just above the surface, so the surface itself is not exposed to the environment. Now, there are various ways to do this. One way, which used to be used in the past, but it's actually a very, very inefficient method, is called ponding. That is, after the concrete sets in a couple of hours. We don't do it initially, but after the concrete sets in a couple of hours, we just flood it with water. So you just take a hose pipe and you spray it with water, and we call this ponding because you basically create a little pond of water on top. This is a very, very inefficient method because the water is going to evaporate very quickly. So you have to keep doing this continuously and keep it moist for at least 3 days. So it's a very inefficient method, uses up a lot of water, generally not used in practice except for very small projects. In practice, what's done now, however, is that we take jute bags, which are fairly cheap and are produced at very large quantities in India as well as in Bangladesh. So these are relatively cheap. They are just dipped in water, so they're made moist, and then they're just put on top of the concrete. So this picture I have over here is from a JPCP construction project where I was present. And as you see, at the end of the day, they finished laying the concrete, they finished sawing the joints, and then they've just put these bags of jute, which are moist bags of jute, on top so that the surface remains relatively moist. By the way, this moist jute cloth in some applications is also called burlap. So don't be surprised in literature if you just see burlap written over there. It's just another way of saying moist jute bags. Now, one issue here is that you need a lot of jute bags. So as you can see over here, you need, basically, if you want to be perfectly efficient, you need as many jute bags as is the surface area of the pavement. Now, as I had mentioned before, we don't construct 2 kilometers, 3 kilometers of pavements at one go. We usually construct a lot of pavements at one given time, particularly over a period of 3 days, which is that critical initial time. We can easily construct tens to even maybe 100 kilometers in a given day. So that would mean you need a lot of burlap, and that can be difficult to get. It's not very expensive because burlap is not a very expensive product, but nonetheless, you do need it in very large quantities. Now, transporting them, wetting them, laying them, and the labor required for that can start making this very expensive. So although this doesn't require any expensive product, unlike chemical curing, but still using them can be quite an expensive application. Furthermore, quality control can be a major issue. What does that mean? If I look at this figure over here, as you see, and this is actually a fairly common application which you see in highways also, the entire surface is not covered in these jute bags. Most of it is covered, but in between, some amount of gap is left. That's inevitable. That's because you don't have enough jute bags. So in this case, you can have quality issues because you aren't uniformly covering it. Secondly, all jute bags are not the same. So depending on how much overlap you're putting, depending on the thickness or the source of the jute bags, depending on how long they were dipped in water, how long it took that after you dipped in water and you laid it on the pavement, was there a time gap in between? All of these things can cause variations in the effectiveness of this jute bag or burlap. So quality control can be fairly difficult to check in this particular case because it's such a manual and physical way of doing it. It's difficult to actually check whether quality control is taken care of or not. So Whereas in chemical curing, that is relatively simpler, but there also many questions exist. So the effectiveness of curing for pavement applications is quite an open question, and there are a lot of different thoughts and a lot of different research going into this area. Okay, so now that we understand what is the source of shrinkage and we understand how we control shrinkage, one thing we have to keep in mind is, due to these inconsistencies, due to the fact that we can't fully control quality in all cases, a certain amount of shrinkage is going to be inevitable. If you don't do anything for controlling shrinkage, then you're definitely going to have a lot of shrinkage cracking. But even if you do your best to control shrinkage, some amount of stresses are still going to develop nonetheless. So when we are working on analyzing rigid pavements and we're trying to estimate the performance, which basically means we're trying to calculate the stresses developed in rigid pavements, it is important for us to be able to calculate the stresses developed as a result of shrinkage. Now, what I'm going to do in the next couple of slides, I'll go through and tell you one particular method. There are several methods for estimating these stresses. We will go through one popular method, which is actually used relatively commonly in the US in their pavement design applications. But I'll tell you what the general principle is. The principle is as follows, that we have a rigid pavement thus. And now, as I said, you're going to have a small part of it which develops a very high humidity gradient. That humidity gradient somehow, and that somehow we'll see today, that humidity gradient is going to be converted to some amount of strain. This we like to call the shrinkage strain, epsilon SH. So we say that because you have a humidity gradient, you have some amount of shrinkage strain which is being developed at the surface. This shrinkage strain, then we assume, is the equivalent of some fictitious shrinkage temperature. In other words, we write epsilon SH, which is the shrinkage strain, which is an actual value that we can measure. We say this is equal to alpha, which is the coefficient of thermal expansion, alpha TSH, where TSH is not a real temperature. It's some fictitious shrinkage temperature. It's not something you can measure. It's not a real thing. But we do this anyway. And then remember, we can measure or calculate epsilon SH. And what we'll see in the coming slides is a method to calculate epsilon SH. After we measured or calculated epsilon SH, we divide it by alpha, and then we get this TSH. TSH is a fictitious temperature, but nonetheless, it's a temperature. We know what to do with temperature. In the previous class, we studied that if we have a non-linear temperature distribution, what do we do with it? How do we decompose it into a TC, TL, and TN component? We saw how to do this. And so all we have to do in this case also is we treat this as another temperature. You add it to whatever TC, TL, and TN had been calculated from the actual temperature, and then continue to do your calculations for stresses. So that's basically the philosophy, is that we calculate the shrinkage strain and then we convert it into a fictitious shrinkage temperature, and then the analysis proceeds as usual as we do for temperature. So really, when it comes down to estimating shrinkage stresses, the real question is, how do we calculate these shrinkage strains? Now, one thing I want to show you, that generally, even qualitatively speaking, what do these shrinkage strains look like? There are basically two models. So first of all, what I have, if I have a layer of concrete and it has a particular thickness, at a very, very thin thickness, that can be something like 25 to 50 mm from the surface, that's the only part of it where any shrinkage strain is going to be developed. Below that, we assume that the relative humidity continues to be around 100%. So there is no shrinkage occurring over here. But it's just in this tiny range where we are actually concerned about shrinkage strains. So there are two ways to look at this. We can assume that there is a maximum shrinkage strain at the surface, and at the point, at this depth H, which sometimes we, by the way, write this as HS, depth of shrinkage. So from the surface, at the surface, you have some maximum shrinkage strain, which we have to calculate. Up to some depth of shrinkage, we can assume that we have a linear distribution. So overall, our distribution is this triangle type of shape. The overall distribution of strain along this cross section then is this non-linear. So it's basically a little triangle on top and then a constant value. So the overall distribution is piecewise linear, which is still non-linear. Or the other value which we can assume is, we can assume that we have some maximum shrinkage strain, and that same shrinkage strain is constant throughout the surf, throughout this depth HS, throughout the shrinkage depth. So in this case, this is by the way strain profile or shrinkage strain profile. So the other option is our shrinkage strain profile can be piecewise constant. So in the first case, it was piecewise linear. In the second case, it's piecewise constant. Both of these, however, so whether it's piecewise linear or piecewise constant, the fact that it's piecewise means the entire strain distribution, this epsilon S, the shrinkage strain distribution throughout the depth is nonlinear. And so we get a nonlinear shrinkage strain distribution. Regardless of which one we choose, however, which distribution we choose, ultimately the question is, how do we calculate this maximum shrinkage strain at the surface? Now, to do that, there are several guidelines and recommendations that we can follow. There is an extremely good document, which is ACI 209.2R08. So ACI, formerly known as the American Concrete Institute, but now it's just ACI International. It's an international organization based in the United States, which compiles a lot of research based on concrete. And they have several books and recommendations on how to analyze different effects of concrete. ACI, like many organizations, including in India, it consists of several committees. ACI Committee 209 examines the effect of shrinkage and creep on concrete. And so they have a particular document, 209.2, and R08 means it was the 2008 revision. That's the most recent revision as of now. So this ACI R209.2 R08 revision is called the Guide for Modeling and Calculating Shrinkage and Creep in Hardened Concrete. Forget creep, that's not important, and we'll not be talking about in this entire series of lectures. But shrinkage is indeed something that we are quite interested in. So this is the Guide for Modeling and Calculating Shrinkage in Hardened Concrete, which is exactly what we're interested in. Now, this document, again, through your institute library, you might be able to get a hold of this document. There might be some other ways you can also get it. But if you open it and you actually look through the document, it's a very interesting document because it gives you a long discussion of different types of methods. So it's not a prescriptive document in the sense it doesn't tell you one exact method to use. It actually summarizes and looks at different methods that have been published in literature and then gives some guidelines on which one to use in which case. Appendix A, interestingly, so not the main document, but actually the appendix of the document, in particular Appendix A, actually gives a very nice summary, and I would argue probably the most comprehensive summary of all these models that you can find in literature. So you actually get a very nice summary of these models. The 4 models which are specified in this latest revision of the document are the ACI 209 R92 model. The fact that you have R92 over here should tell you that it's a fairly old model. That's from 1992. You've got the Bajant and Baweja B3 model, which is the one which we'll talk about today. You've got the CB MC 1999 model and something called the GL 2000 model. So we're not going to talk about 1, 3, and 4 in class. I welcome you to get a copy of this document, look through it, and understand these yourself. They're quite interesting in how they do the analysis and the assumptions. What we will focus on in today's lecture is A2, which is the Bajant Baweja B3 model. How can we use it? Basically, again, we want to calculate epsilon SH. We want to calculate what is this maximum shear strain at the surface. And from there, we can then go on to calculate what are the stresses developed. So in the next couple of slides, I'm going to show you the Bajant and Baweja B3 model, what are the equations involved in them, and how can we use them to calculate this epsilon SH. Okay, so these are the different models which we'll look at. Before we look at the models though, we should have a sense of when these different models apply. Why do we have these variety of different models? The basic reason is you have to understand the reason that shrinkage is happening in the first place is because the concrete is drying. Now, the concrete is drying due to 2 factors. One is, of course, you have some amount of moisture loss to the environment. But you also have the concrete itself, which is using up the moisture. The reason you have water is for the hydration reaction. So water is consumed in the hydration reaction. So these models which are trying to estimate this maximum strain which is developed, these models then have to take into account not just the humidity, but they also have to take into account the type of concrete and the type of cement that we have. And so for that, what we have in this from ACI 209, this table which shows you what is the range of applicability for different models. So example, we have something called FCM 28. So FCM over here is compressor strength, mean compressor strength. So FCM 28 just means at 28 days. So depending on the general range of the compressor strength, depending on, for example, the cement content, the W/C ratio, depending on the type of cement which is used, depending on the curing time, TC, so TC stands for curing time, depending on the curing time and the mechanism of curing. So whether you're moist cured, which is you're curing by putting moisture, or whether you're steam cured, that curing is quite through by putting the concrete in steam. This is not done for pavement applications, but depending on the different type of paving curing mechanism and amount of curing, different models are applicable for different ranges. This Bajant and Baweja model, for example, which I've put here, for example, FCM is valid from 17 to 70 megapascals. Generally, for rigid pavements, we would like to use around 40, maybe 50 megapascals. That's generally the range that we're interested in. So the Bajant and Baweja model fits well in, and you can look at the other values as well. They generally also apply. So usually what we've seen for pavement engineering practice, the Bajant and Baweja model is a useful model, not that the other models cannot be used. Furthermore, also from the same ACI document, here is a diagram they provide for the B3 model. So on the x-axis, what they have is the measured shear shrinkage strain, epsilon SH, and here the calculated value based on the model. And here you see that the fit is not that bad. Of course, at relatively lower values, down here, for example, the fit is quite good. Once you go to higher values of the strain, it starts to go, you get a lot of dispersion. This is generally what you'll see in a lot of these studies, that you're not going to expect an R square of 0.9 or something of that sort. But generally, because a large percentage of the data, especially on the lower side of the strain, is around this reference line, this 45-degree line, generally it's been found that the Bajant and Baweja model is fairly good and can be used, particularly for pavement applications. Okay. So again, let's go into what exactly this model. In the next lecture, we will do a detailed calculation. So I don't want to go through all the mathematics today, but I definitely want to show you some of the equations so you understand what are the different factors involved and what calculations are involved. At the end of the day, we are interested in calculating this mean shrinkage strain, epsilon SH. Now, epsilon SH, as you can imagine, is going to be a function of time. Why is that? Because the amount of drying is changing over time. As I already mentioned, that shrinkage occurs due to some amount of drying. That's also a factor of time. During the time when curing is happening, that is, you've locked in the surface or you've put these jute bags, then you don't have a moisture gradient. So these shrinkage strains, which are caused by moisture gradients, they don't develop during curing time. So therefore, the shrinkage strain depends not just on the time, it also depends on the amount of time during which curing has taken place. There is also a question on efficiency of curing, etc. We'll talk about that. The basic assumption of the model is as follows, that the shrinkage strain is basically can be decomposed as some constant component. So this is what's written as epsilon SH infinity. Note that there is a negative sign here. This negative sign needs to be there. You should not forget to add this. So this epsilon SH infinity just says what is the long-term shrinkage. So after a very long time after curing, what is the amount of shrinkage strain that would be developed? That's one part of the equation. The other part of the equation, which actually tells us how is the shrinkage changing over time after curing time. So only after TC, hence T minus TC. That, as I show, it turns out it assumes that this is some type of a hyperbolic tangent function. So we'll see what this looks like in practice. So in this term, what we see over here, this S of T minus TC, I'll show you what it is, but it's a relatively simple term. KH depends on the amount of humidity. We'll also have a look at that. But we have this particular term, epsilon SH infinity, which is after a very long time. What is the asymptotic or the final value or the long-term value of the shrinkage strain which is developed? That's a value that has to be calculated. What Bajant and Baweja, ultimately this value depends on the type of concrete mix that we have and its strength. That's what the model says. So basically what we have is that epsilon SH infinity is equal to some epsilon S infinity, some parameter, and there is a correction factor which takes into account the elastic modulus. So E stands for elastic modulus, EC stands for elastic modulus of concrete, M stands for mean. This number 607 actually tells you after how many days. So the point is that at the early age, not only is the strength of the concrete changing, but the elastic modulus of the concrete is also changing. So when we talk about the strains which develop, we also have to put in a correction factor for the elastic properties or the elastic modulus of the concrete at that early age or at that point of time. So this particular term, ECM 607 by ECM tau C plus tau SH, I'll define tau SH in a second. This is basically some correction factor which takes into account that the elastic modulus of the concrete is changing at early age. Now, ECM, which is the elastic modulus as a function of time. So that's what ECMT stands for. This is shown empirically using this equation. So ECMT is ECM28, the 28-day elastic modulus, which is generally something we measure for concrete, or at least we estimate from, say, FCK. This is T divided by 4 into T divided by 4 plus 0.85 T square root. Don't forget the square root. So there's this T in the numerator, T in the denominator, and there's a square root. Fairly non-linear function. So what this says is that the elastic modulus is a non-linear function of the elastic modulus of time, which depends on the elastic modulus at 28 days. So epsilon SH infinity, which is what we're interested in, this is equal to some negative epsilon S infinity into this correction factor, which we can calculate. We have to define tau SH. I'll define it in a second. And then we have this. So what is epsilon S infinity? Epsilon S infinity is basically telling us that corrected for the rate of change of properties of the material, taking that into account, what is the long-term shear strain which is developed in the concrete. The long-term shrinkage strain which is developed in the concrete, not shear, shrinkage, it's basically going to be a function of the material properties of the concrete. So the BW model, the B3 model, we have this empirical equation, and I'll define the terms in a second, but it's negative of alpha 1 into alpha 2 into some 0.019, it's an empirical coefficient, W raised to the power 2.1. This W is the water content, into FCM 28, that is the compressor strength at 28 days, raised to the power of minus 0.28 plus 270. This is all a strain, so into 10 power minus 6. So basically telling us it's a microstrain. What are these terms, alpha 1 and alpha 2? So it's over here. So alpha 1, it depends on the type of cement. So if you have type 1 cement, which is generally the case even in India, type 1 cement, alpha 1 is simply equal to 1. And then depending on the type of cement, you have different values. Alpha 2 is a function of the curing method. So if it's steam cured, you see that the multiplying factor is 0.75. Steam curing is a very efficient form of curing. So we basically can reduce the long-term shrinkage strain by 25% if we do steam curing. But steam curing is simply not practical for rigid pavement, so we don't use it. If it's cured in water at 100% relative humidity, that's basically using burlap or jute bags. That's basically what we do. Then this alpha 2 is basically equal to 1. There is an option of sealing during curing or normal curing with protection against drying. This is chemical curing. If you use chemical curing, then the strain surprisingly actually goes up. So it becomes 1.2. So generally, when we do analysis of rigid pavements, one of these two is applicable. In India, most likely, this curing using this jute bag or burlap is what's used. So in general, if you don't know anything else, we generally take alpha 1 is equal to 1 and alpha 2 is equal to 1. So that's very nice. We took care of these two values. W, as I already mentioned, is the water content. This is going to be in kilogram per cubic meter. FCM 28 in megapascals. And from there, you can calculate the epsilon S infinity. Similarly, ECM 28 is a value that you have to know, but it can be estimated from FCM 28. We talked about that in module 1. And then you simply calculate this correction factor with this tau SH. Okay, what is tau SH? Tau SH is basically, it's a half-life. So basically, whatever is what we call this long-term period, where over the long term, we have this epsilon SH infinity. How many days does it take after curing is done? So after TC, how many days does it take for it to reach half that shrinkage value? That's what we call tau SH. Another way to put it, it's some type of a characteristic time of development of shrinkage. But basically, it's the half time of the development of the shrinkage strain. There is a formal formula to this, which is shown over here. I'm not going to go into a lot of details of this formula because when we do an example, which we'll do in the next class, but when we do an example for this, there are generally recommended values which are used in practice. Now, a lot of this is based on AASHTO in the US, which provides these recommended values. So we generally just use a recommended value of tau SH. And then S of T minus TC, which is the value we need, which is that expression which tells us how the shrinkage strain is varying with time. This is basically this hyperbolic tangent function of the square root. Another common mistake students make, it's of the square root T minus TC divided by tau SH. Important, it's T minus Tc, and the square root is not going to admit a negative value. So if T is less than Tc, there is no shrinkage involved. So shrinkage strain is simply 0. So we only start calculating this after Tc, after the curing is completed, generally 3 days, but it could also be 7 days, depending on the application. If you go back to this equation, you'll see that there was also this term Kh over here. So this epsilon Sh infinity, we saw how to calculate that. S of T minus Tc, we saw the function form that. We also have this Kh. Kh is simply a correction factor of the ambient humidity during the time of construction. So if the ambient humidity is exactly equal to 1, then your recommended use of value of Kh is of minus 0.2. If, however, it's between 98% and 100% humidity, then you are recommended to use this particular formula to calculate it. Note here, the humidity is specified as a fraction, not as a percentage. And if it's H, the ambient humidity is less than 0.98, then you use some other function. So this is an empirical piecewise function which is provided just to provide a slight correction factor to take the ambient humidity into account. So to summarize, the Baweja model, as we see, it basically shrinkage depends on the ambient conditions, the type of concrete or cement that we have, and the curing that we apply. So the curing that we applied is taken care of, and the type of cement is taken care of in this alpha 1, alpha 2, and generally in this epsilon S infinity, epsilon SH infinity term. The rate of the ambient conditions are taken into account through this Kh factor, and the rate at which it's changing, or the actual functional form, is this S of T minus Tc, which is this hyperbolic tangent form. Okay, now so we'll do a detailed example in the next class, but if now we can calculate epsilon Sh, what Bajant and Baweja assume then is that this epsilon Sh is going to occur over this depth Sh, which is the shrinkage depth. So you have some epsilon Sh at the top. You have a value of 0 at HS and below that. So this entire depth is H. And then you have a triangular distribution. So it's very important, assuming that it's a triangular distribution. And then if we try to calculate what is the equivalent temperature distribution, the equivalent linear temperature distribution that comes from this, we basically get this equation over here. Again, it's a function of time because epsilon Sh is a function of time. You can do this by performing that integration which we talked about in the previous lecture where we talked about temperature. So it's the same thing. I'm not going to go through the details, but this is basically the equivalent form which you get. Here again, note the required values. We have the epsilon Sh as a function of T that we get from the Bajant and Baweja model. We have this Sh, which is the depth of shrinkage, that is generally 25 to 50 mm. We generally just make an assumption of what is a reasonable value to use. And of course, we have H, which is the thickness, because this temperature distribution is also going to depend on the thickness. So we get this temperature distribution, and this is the, note you'll also have an alpha over here, which is the coefficient of thermal expansion. So we use this formula then to get this TSH. That is an additional temperature difference. So this is an additional delta T temperature difference. This additional temperature difference then, we have to include it in the temperature difference that we have for temperature previously. So previously we saw we have a nonlinear temperature distribution in pavements. Part of this is going to turn into a linear temperature distribution like this. We have to add this linear temperature distribution from shrinkage to this. So effectively for our pavement as a whole, our delta T, the linear component, is going to be delta TL, which we get from by decomposing the temperature distribution into its components, plus this TSH. And that's going to be a function of T. So this really should be a delta TSH. So this is ultimately, this is the value that we're going to get. This delta T then generates a certain amount of curling stresses, which then we take into account in our calculations. Note, there is no eigenstress developed, although this is non-linear. If you actually do the calculation, you see that there's no eigenstress component coming out of this. So there's no eigenstress which we take into account over here. Okay. So in the next lecture, we will see a detailed calculation for all this. So I know it was a lot that we covered and many concepts to think about. We will bring it together and we will do a detailed calculation for a problem in the next lecture. But before going to the next lecture, I did want to talk about one other factor related to temperature again, which is called built-in curling. We made a very important assumption. We kind of implicitly stated it, I didn't explicitly say it, but we made a very important assumption. If you recall from the previous lecture on temperature distribution, I said that all temperature distribution is relative to some constant reference temperature distribution, T naught. So if I had a pavement where this reference, if the actual pavement temperature was equal to the reference temperature, then my stress is going to be zero. That is a definition of zero stress. So my zero stress or my reference configuration is simply when my pavement has a temperature profile which is equal to a constant temperature, and that constant temperature is the reference temperature. So when T of Z is equal to T naught, then by definition we say that sigma is equal to zero. That's what we call the reference condition. Thus, we assume in doing all our calculations for stresses, whether it's curling stress, whether it's eigenstress, we assume that the reference stress state is a constant temperature. And what value of T naught? So far, I never actually defined the value of T naught, and that, to be fair, it doesn't actually make too much of a difference for the analysis we've done so far. What is the value of T naught we should use? In general, in practice, the average annual air temperature is used. There is no good reason why this is the case. After all, the pavement is going to be there when it's initially laid. The reference temperature is at whatever temperature it was laid at. There is no very good reason why this is used. It's just based on practice. So the average annual air temperature is usually used as a guess for the reference temperature. And then we assume that all the stresses are with respect to this constant reference temperature. But the question we should think about is this actually correct? Is this really how the pavement behaves? Well, think again about the early age behavior of the pavement. That is, when we say the pavement is in its green state, that's generally 3 days, up to 3 days from the point at which the pavement was laid. Consider what's happening at those early age conditions. So during those early age conditions, particularly initially when we just laid the pavement, the concrete is still in a fluid. Or another way to write it is the concrete is plastic. What plastic basically means is it can undergo any amount of deformation for basically the same amount of stress. So at an early age, when we lay the concrete, it is still exposed to the environment, which means even that early age concrete, this plastic concrete, it is also going to acquire a nonlinear temperature distribution. Now, what I had said last time is when the slab acquires a temperature distribution, it's going to try to assume a certain shape, and that shape is it's going to be restrained from assuming that shape, and that's going to give rise to stresses. That is true for elastic materials. However, in a plastic material, the concrete is free to assume whatever shape it wants. Even if that shape is restrained, it's not going to generate any additional stresses. So the temperature distribution which is generated at that early age, when the concrete is still plastic in nature, the temperature distributed at that early age does not lead to any stresses developing. Once the concrete hardens, so the concrete has at that plastic stage has acquired some nonlinear temperature distribution. But when it acquired that temperature distribution, it does not have any stress. So there is a temperature distribution, but there is no stress being created because it's in plastic condition. But the concrete is continuing to harden. The hydration process is continuing. Because it's hardening, once it reaches set, once it becomes an elastic material, then this concrete initially has zero stress. But the temperature distribution is not constant. It is whatever temperature distribution was developed during those early age. So really, the zero stress configuration, the temperature distribution at which the stresses are zero, is not a constant uniform temperature configuration. It is actually a configuration where you have some nonlinear stress which has developed and has become what we call locked in, or more generally, it has become built in. So it's a temperature distribution which was acquired by the pavement when it was still plastic. Because it was plastic, no stresses would develop, but there is a temperature distribution now. That phenomenon, where you have some temperature distribution which has been built into the pavement, it is not causing any additional stress. But when we are doing our analysis, our reference condition changes. So our reference condition is no longer T is equal to T naught. Our reference condition is T is equal to some temperature distribution. And so our stresses has to be calculated with respect to that reference condition and not with respect to the reference condition of T is equal to T naught. This phenomenon is called built-in curling. It has been found that if this particular phenomenon of built-in curling is neglected, if we don't take into account in our calculations, we can make significant errors in our stresses. I'll show you some estimate of what a built-in temperature difference is, but it can make a very large difference to our performance estimate. We can actually lose several years of performance as compared to our design if we don't take this phenomenon into account. So it's very important that this is taken into account. Okay, so thus, once the concrete has set, it has a temperature distribution built into it. And this temperature difference is called built-in curling. Now, in India and some European countries, this has a slightly different name. It means exactly the same thing. It's sometimes called zero stress temperature gradient. So it is a temperature gradient. When it says gradient or difference, it's instantly assuming that some linear temperature distribution has been built in. So built-in curling is a general term. It means that at an early age, we had some non-linear distribution that was kind of built into the pavement. When we say zero stress temperature gradient, we are assuming that non-linear distribution, that temperature distribution was actually linear. That initial built-in temperature distribution was linear. So there's a subtle difference between the two terms, built-in curling and zero stress temperature gradient. Nonetheless, to speak in general terms, we can just say that these two are more or less equivalent to each other. They're talking about the same phenomenon. They're just characterizing it using slightly different assumptions. So this is called built-in curling, or in India, you'll hear the term zero stress temperature gradient. It is the temperature gradient that is present at the reference state. That it is the temperature gradient at which no stresses exist, even though there is a self-hit, even though there is a restraint, no stresses exist. And then all our stress calculations have to be with respect to this reference state, not to the previous reference state of T is equal to T naught. So to explain it more generally, if we did not consider this, if we did not consider built-in curling or zero stress temperature gradient, this is our reference state. That is, the slab is perfectly flat. But if we do consider it, and we should consider it, if we do consider this condition, then maybe the slab looks like this. Now, generally what you'll see here, this has a slight curvature upwards. And that's generally also the case because it takes a couple of hours for this to set. So if the concrete has been laid during the day, and that's not an uncommon thing. If the concrete has been laid during the day, then you're going to have some amount of expansion of the top. So you're going to acquire this upward curvature type of shape. So, but if the concrete is laid during the night, then you can have a different reference condition. It can look like this. So actually figuring out what the reference condition is quite complicated. I'll talk about that in the next slide. So these additional stresses due to the presence of this has to be taken into account. So if we don't consider this, we'll make significant errors in our calculation. So how do we actually calculate it? Well, if we wanted to model built-in curling, that we actually wanted to very accurately estimate built-in curling, what we really need to do is we should not be modeling our material, which is concrete. We should not be modeling concrete as an elastic material at all. Instead, we need to model the dynamics of concrete. That is, we need to model the concrete as it develops from fresh state to the point when it goes to its hardened state. We need to model that entire life cycle. During that time, we need to couple those with temperature. So we need to see that as the properties of the concrete are evolving, and depending on the environmental conditions, etc., how is the temperature of the concrete changing? And that then gives us a very accurate estimation of the built-in curling. Now, that's all theoretical, that's all well and good, and indeed, it is an open area of research. And I myself have been involved in some research where we did exactly that. In practice, however, as those who are working as practicing engineers, this can be quite difficult to do. Anything which goes beyond linear elastic analysis is a difficult thing to do for us. So generally, we don't do it. So then what do? We need to estimate it. So what do? Well, as we are good engineers, since we don't estimate it, we choose not random, but we choose a nice design value and decide to stick it in there anyway. So in practice, we assume some design value of delta T. That we assume that, first of all, we assume that this built-in temperature distribution is linear. That's a big assumption. It is not linear in practice. It is non-linear. We assume that this built-in temperature distribution is linear. For this, we have some T top minus T bottom, which is delta T. We have some T top minus T bottom with delta T, and we add this. So we call this the built-in temperature difference, BITD. This is built-in temperature difference or zero stress temperature difference. We add this zero stress temperature difference to the transient temperature difference. So from our transient analysis, and we have a non-linear distribution. So if I call this BIC, if I have this non-linear temperature distribution, I already saw that I can decompose it into 3 components, right? This particular component, which I previously called delta TL, I will add this to this, I will add delta T BIC, and then this becomes my reference configuration. And now I calculate my curling stresses with respect to not delta TL, but delta TL plus delta T BIC. I add these two and then I do the calculations for stresses. So in practice, that's all we do. We have our transient temperature difference, and to that, we add this built-in temperature difference. We take that as the total temperature difference for curling, and then we calculate curling stresses from that using a variety of techniques. So the real question is, what is delta TBIC? If we don't want to go through this long process of modeling the dynamics of concrete development, then what value can we use? It turns out there is a whole variety of answers for what you can use. AASHTO in the US recommends a value of delta T is equal to minus 5.6 degrees Celsius. IRC 58, which is the Indian code, uses a slightly different value of minus 5 degrees Celsius. And if you actually look up literature on this and various design codes from around the world, there's a whole variety of values. Indeed, there is one interesting paper which I'm aware of, which actually suggests using a different value during the day and a different value during the night. Again, this is a built-in value. This is whatever value was present once the concrete hardened after construction. The fact that we are recommending a different value during the day, different value during the night, is not mechanistically consistent. It's not what's happening in physics, but it's a nice way to explain some of the data which has been observed. The truth is that all of these techniques are based on limited empirical data. Some data has been collected, and we are trying our best to explain the observations, but none of the models as such is correct. If you want a so-called correct model, we have to go through this long way of modeling the dynamics, which for now is an open area of research. Okay, so to conclude, in today's lecture, I showed you about built-in curling as well as moisture. We looked at the Bajant and Baweja model to calculate this TSH. And this TSH is really delta TSH. We calculate this value and then we add it to our delta TL, and we use that as some kind of a curling stress. To that, we also calculate delta TBIC to take built-in curling or zero stress temperature difference into account. We saw how to do all these calculations. These two calculations we saw today. Delta TL calculations we saw in the previous lecture. And then the first lecture in this series was related to this phenomenon of climate in general. I gave you a lot of maths. I gave you a lot of formulas. I understand that all of it is not clearly apparent. So when we meet in the next lecture, which is lecture 14, we will do some solved examples where I'll show you exactly how to do these calculations for delta TL and delta TSH. We will not go into calculating the stresses yet, because for that, first we have to understand the finite element method, which we'll do in module 3. So I will see you in the next class for some solved examples. Thank you.